Okay, here's,
Quick
any questions
question.
on this one?
Yeah.
Yeah.
So you have the c times x to the fourth,
Yes,
but if c is just any constant
yes.
times anything, it's still just some constant, correct?
No, no, that's not a constant x to the fourth. C is the arbitrary
You
constant.
want us to note where,
Yeah.
like, C1, you make it C1, go C1 equals C times X to the fourth, if you want to just put C there.
No, no, it's a big mistake.
But you can't
C
put
is
it
an
as-
arbitrary constant, but is x to the fourth a constant?
No.
No.
But if you note it, like, if you make that C on the bottom C1, and then note C1 equals C times X to the fourth.
No, that, well, you could do that, but that's bad
That's not-
notation,
that's
right?
not- that's bad
Because we think
notation.
of C's as constants, yeah. You see what I'm saying? Yeah. You could say C1 and C, where C is Cx to the fourth, but I wouldn't do that. It's a bad notation, okay? Usually when people have, in differential equations, they have like letters like this. Those are usually parameters, okay? So I would keep everything, let the C's be constants. If there's explicit X dependence, call it X to the fourth.
So that one, because it's x to the fourth, you leave it, but if it was like times 3,
Yes,
C, you just
yes,
change
yeah,
it to
yeah,
C.
exactly. 3C is the same as the arbitrary constant. And of course, what would happen is that if you had initial data, you get the same answer at the end anyway. Okay. So it's only things when you have, like, sometimes we'll integrate, we'll have x squared over 2, y squared over 2, and put a c on the right, and then we multiply by 2. Yeah, 2c, if c is arbitrary constant, that's another arbitrary constant. You just relabel it.
Okay.
But here, it's a big difference. It's x to the fourth, and that's your variable. So you don't want to absorb that into the c. You can't.
Okay.
Okay. Good question. Okay. Glad we got that out of the way. Okay. Now, let's see. Another example. Now this is one where you have to be careful. When I've been integrating things like log x, 1 over x, I put log x, okay? And what happens many times is you have to be careful, when you do the integral of a logarithm. This example over here is a good illustration. This is the example number 4. Yeah. Suppose I have x squared minus 9 dy dx plus xy is equal to 0. Right? That's the first order linear equation. Right? It's not separable. Okay, it's something which, had we not gone over this technique, you wouldn't be able to do. But the idea is to recognize that it's first order and it's linear. Right? So minus 9 dy dx plus xy is equal to 0. Okay, what's our first step? Put it in the standard form, right? So we've got dy dx plus x over x squared minus 9 times y is equal to 0. Okay. Now I have to consider two kind of cases over here because when I, what's my p of x over here? This is my p of x, right? When I integrate that p of x, right, which is the next step, do I get log of x squared minus 9, log of 9 minus x squared? I have to be very careful. So case 1 that we would consider is assume the absolute value of x is greater than 3. Okay? What does that mean? That means that x is greater than 3 or less than minus 3. In both cases, x squared would be greater than 9. So the denominator will be positive. And this happens a lot when you have differential equations and you've got a coefficient of the highest derivative that may go to 0 someplace. It's called a singular differential equation. And what's going to happen is we're going to find out that we have to basically do two separate solutions. One when the absolute value of x is greater than 3, and one when it's between minus 3 and plus 3. Okay? Okay. So, if that's the case, then the integral of p of x dx is what? Log of x squared minus 9. I think there's a half in there, right? Let's see. Right? So when I differentiate the log, I get 1 over x squared minus 9 times a 2x. So I need the half in there to get x over x squared minus 9. And again, remember we're going to take the exponential of that, so you got to somehow get that half out of there, okay? And we remember that from our laws of logs, the log of x squared minus 9 times a half is really the log of that to the 1/2 power, or the log of the square root of x squared minus 5. And I've seen many, been teaching this for many years, and unfortunately what happens to many students, they don't remember the laws of logs, and then when they get the integrating factor, which is very simple many times, they can't do it because they have e to the 1/2 log, right? And they don't know what to do with it, okay? So you want to do things like that, okay? Okay, so the integrating factor phi of x is what? I just do the exponential of that, and then it's beautiful now, right? Because the exponential of the log is the function itself. So it's the square root of x squared minus 9 in this case. Okay. Okay. Continue over here. We multiply the equation through by the integrating factor, and remember, it's this one that we multiply by the integrating factor. Okay, so when I do that, I get radical x squared minus 9 times dy dx, right? Okay. And now what happens over here? Radical x squared minus 9 over x squared minus 9 gives me a radical in the denominator, so I get x over radical x squared minus 9 times y equals 0. When radical x squared minus 9, I get the x, radical over that, radical, okay? Now, this is why it's good to, to remember the theory a little bit, because if you looked at that, you say, my God, you're telling me that's an exact derivative? It's d by dx of what? But remember, we know what it is, right? It better be the form d by dx of the integrating factor, which was this, times y. Actually, you can get it from the first term over here, if you don't remember that. But, like I said, to check your algebra, if you haven't made a mistake either in integration or in manipulation, do this quickly in your head, make sure you get that back. Product rule. I get radical x squared minus 9 dy dx, right? Then I get plus y. What's the derivative of that guy, right? It's the derivative of x squared minus 9 to the 1/2, which is 1/2 x squared minus 9 to the minus 1/2 times 2x. The 2's cancel. You do get that. Okay? You may want to do that, I went pretty fast on that, okay? But believe me, when you do the product rule, you do get that, and that's what the theory says. Great. So now I get radical x squared minus 9 times y is an arbitrary constant, right? And therefore, the solution is y equals arbitrary constant over the square root of x squared minus 9. And remember, this was for the absolute value of x greater than 3. Okay? I'm not going to go through the algebra, but you could do the same thing over here. Let me go up to a point at least and show you how to do it for the other case. So that's case 1, right? There's the solution for absolute x greater than 3. Okay, and you can see it's fine because there's no imaginaries in there, right? When absolute x greater than 3, the thing in the denominator is always positive and real. That's really redundant. Okay. What about case 2 now? Absolute value of x less than 3. Okay? There are various ways of doing it. Okay? What I would do basically is that I want to make x squared minus 9, let's see, 9 minus x squared. So let's just rewrite the equation a little differently. So you get dy dx. Let's write this now as minus x over 9 minus x squared, right? See, because then I have, that's obviously the same, times y equals 0. Okay, you can go through the same thing again, get the integrating factor, but now your p of x, notice is x over 9 minus x squared with a minus sign in front. See, and the idea is, let's just do it over here. Okay, now the p of x, remember you have to be very careful, that's the y coefficient, it's minus x over 9 minus x squared. So I do the integral of p of x dx now, in order to get a real thing over there, I want 1/2 the log of 9 minus x squared, right? So I differentiate that, I get the 1 over 9 minus x squared times negative 2x, which is that, which is the same as this, the logarithm of the square root of 9 minus x squared, okay? And I will go through the rest. Obviously, the integrating factor now is going to be radical 9 minus x squared. You go back to this equation, do the whole thing again, solve it. It's exactly the same as you've done over here as far as the steps go. And you'll find that the solution there is y equals a constant, I'll call it c prime, to make sure it's not the same, over the square root of 9 minus x squared. This is for absolute x less than 3. Okay. So you just have to be very, very careful over here, right? This thing is only for absolute x greater than 3, so that the thing downstairs is always positive, and the same thing over here. And apparently we don't have a solution at x equal to 3 or x equal minus 3. It blows up. And if you take an advanced course of differential equations, you know that because these are what's called singular points. But let me now just kind of sketch a graph. I'm not even doing it on the computer. We can do it by hand. The book doesn't have this, and I thought it was interesting. I'm going to have a graph over here for this problem of 3 functions. First, I'm going to graph p of x, right? Okay, the p of x basically is x over x squared minus 9. Okay? And there's going to be an asymptote, right, over here at x equal to 3. There's another asymptote, right, when x equals negative 3. Right? This function is going to blow up over there, okay? And if you graph it over here, you're going to get something like this. You'll get over there, and then it's going to go like this. It's an odd function. It goes like that. And then you'll find out over here, it graphs like that. And over here, to the left of that asymptote, it graphs like that. So there's the function p of x, the coefficient of y in the differential equation, right? It blows up at plus or minus 3, okay? And we have a graph between minus 3 and plus 3, and to the right of 3 and to the left of negative 3. Undefined, again, at 3 and minus 3. And what's interesting is that I'm going to graph now the solution y, and this singularity, so to speak, that occurs at 3 and minus 3 carries over to the solutions, as you can see, okay? Let's look at the solution, okay? That was p of x over here. Now I'm going to graph the solution to the differential equation, y versus x. Okay, we know we have asymptotes again at x equal to 3. We got another asymptote over here at x equal to negative 3. Okay, and the solution basically actually goes like this. See, when x is equal to 0, this becomes something over 9, something, some constant, whatever it is, okay? So it almost looks like a parabola between there and there. And then if you go to the right of x equal to 3, it looks like that. And to the left of x equal to 3, it looks like that. Okay? So it's very interesting, okay? P of x had these singular points at 3 and minus 3, okay? So its graph obviously had these gaps. And that's reflected in the solution. Between minus 3 and plus 3, the solution looks like that. And to the right of 3, it looks like that, and to the left of negative 3, it looks like that. And that just comes from these expressions that we have over here. Okay, if you want to graph it, just as c equal to 1 or something. Changing c just scales it, right? So it doesn't make the qualitative feature of the graph is the same. Okay. Okay, this one I want to show you a plot of. Try to be efficient over here. This takes time. Just get started. We've got 2 more examples. Okay. Example number 5, I guess. So the differential equation is dy dx plus y is equal to x. Again, it's not variable separable, right? And let's do an initial value problem. I want y of 0 to equal 4. y dx plus y equals x, and it goes to the point 0, 4. Okay. Okay, this one looks simpler than the other one, right? What's the p of x now, basically? It's in the standard form, so p of x is equal to 1, right? Remember, it's dy dx will give us 1. Okay, the integrating factor is e to the x, right? So let's just multiply by e dx. I get e dx dy dx plus e dx times y is equal to x e dx. Okay. If we've done things correctly, the left-hand side should be d by dx of the integrating factor times y. And sure it is, right? Product rule. E dx y prime plus y e dx, that equals x e dx. Integrate both sides. We have e to the xy on the left, right? What's the integral of x e dx? We did that earlier. Does someone have that? Was it x minus 1 e dx?
X e dx times x minus 1, right?
Can you just look it up and make sure it's right? I think it's something like x minus 1 e dx. Is that right? Just check.
What is it? E to the x times x minus 1.
Okay, good. Okay. Now, again, plus an arbitrary constant. Right? Now, before we solve for y, let's plug in the initial data and see if we get the value of c. It says when x is equal to 0, y is equal to 4. So exponential of 0 is 1, so that's 4, right? When I plug in x equal to 0 over here, I get a 1 and a negative 1 plus c. Is that true? Yep. Okay, so c is equal to 5. Okay? So, we have, therefore, e to the x times y, right, equals x minus 1 e to the x plus 5. Okay, now we can just solve for y. Y by e dx. We get x minus 1, right,